Welcome. This is a review video for the test on triangles, the triangle inequality, exterior angle theorem, Pythagorean theorem, all that good stuff. So I'm going to be going through one of the review packets. If you're struggling with these problems, I encourage you to watch some of these explanations, pause the video, and see if you could do them on your own and come back to see if you get the same answer. Okay, for number one. In the diagram below of isosceles triangle ABC, the measure of vertex angle B is 80 degrees. If AC extends to point D, what is the measure of angle BCD? So the measure of angle BCD. That's the angle they're looking for right there, the exterior angle. Now I know that in an isosceles triangle, two sides are congruent. That's what these marks mean. But that the angles opposite them are also congruent. So those are the base angles. So I'll label each of those as x. So I know all of the angles in a triangle need to add up to 180. So I'm going to take 180 and subtract off that 80 from the vertex angle I already have to get 100 degrees. And since both the base angles need to be congruent, if I divide 100 by 2, I'll find that both those base angles need to be 50 degrees. Now the reason why that's useful to us is because if we look at this 50 degrees right in here and angle BCD, we can notice that together they form a straight line, so they're a linear pair, which also makes them supplementary. So I'm asking myself, what angle do I need to add to 50 to get 180? So I can subtract 50 from 180 and get 130 degrees. So the measure of angle BCD equals 130 degrees. Number 2. Vertex angle A of isosceles triangle ABC measures 20 degrees more than 3 times the measure of angle B. Okay, before I even keep reading, I'm going to draw a triangle. Because they're describing an isosceles triangle, so two of the sides are congruent and the two base angles are congruent. And it says there's a vertex angle A, so I'm going to put that at the top here, ABC. That measures 20 more than 3 times the measure of angle B. So before I can write an expression to represent the measure of angle A, I first need to let the measure of angle B equal x, because they're defining the angle A with reference to angle B. So that's 20 more than 3 times, so 3 times the angle B, plus 20. So that's the measure of my vertex angle. And they want me to find the measure of angle C. But remember that the two base angles are congruent, so if the measure of angle B is labeled as x, we can also label the measure of angle C as x. Now we know all the angles in a triangle add up to 180 degrees, so we could set up this equation right here, combine some like terms to get 5x plus 20 equals 180. If I subtract 20 on both sides, we're left with 5x equals 160. And if we divide 160 by 5, we find that x is equal to 32 degrees. And since we labeled the measure of angle C as x, the measure of angle C is also 32 degrees. For number 3. In the diagram below of triangle GJK, H is a point on GJ. HJ is congruent to JK. So I'm going to mark that in the picture right now. HJ is congruent to JK. Okay, and the measure of angle G equals 28, and the measure of angle GJK is 70 degrees. Determine whether triangle GHK is an isosceles triangle. So remember, an isosceles triangle has two congruent sides and two congruent angles. Now, they didn't really give me a whole lot of information about sides here, so I'm going to work off the fact that maybe we could prove that two angles are congruent or that two angles aren't congruent in the triangle GHK. So that triangle right there. Okay, so the first thing I notice is that in the small triangle on the right, I've got two congruent sides, which also means that there are going to be two congruent angles across from those sides. So I can do the same thing I did in the first problem, where I take 180, subtract 70, because all of the angles in a triangle must sum to 180 degrees, get 110 degrees. And since there are two congruent base angles, I can divide that 110 by 2 to get 55 degrees for both these angles, this angle right here and this angle right here. Again, I'm always trying to look for supplementary angles or some sort of triangle angle sum to help me out here. And I notice that angle GHK and angle KHJ are supplementary because they form a straight line together. They're a linear pair. So if I take 180 and subtract 55, I get 125 degrees, or the measure of angle GHK. Now, in order to find the last angle of that triangle, all we need to do is add up 28 and 125 to get 153, and subtract 153 from 180 to find that missing angle, and we find that the missing angle is 27 degrees. So it asked if triangle GHK is an isosceles triangle. Since none of the angles are congruent, we can say that no, triangle GHK is not isosceles. Reason being is that an isosceles triangle has two congruent base angles, but here all our angles are different, so this is actually a scalene triangle. It's close, but not quite. Number 4. In the diagram below of isosceles triangle ABC, AB is congruent to CB, and angle bisectors AD, BF, and CE are drawn and intersect at X. If the measure of angle BAC, so this whole angle right here, is 50 degrees, find the measure of angle AXC. So I'm looking for this angle right here. Okay, they tell me it's an isosceles triangle with this side right here congruent to this side right here. So I know if angle A is 50 degrees, that angle C will also be 50 degrees. But they also tell me that AD is an angle bisector and that BF and CE are as well. Remember that an angle bisector splits an angle into two congruent parts. So rather than using that 50 degrees there, I'm just going to measure each part as 25 degrees instead, because that might be a little bit more useful to us. And since angle A is the same thing as angle C, I can label that 25 and 25 here as well. Now notice that in the angle we're looking for, right there, if we look at this triangle AXC, we're really only missing one angle. Two of the angles are 25 and 25, and that green angle right there, which is what we're looking for, we could just label that as X. When you add up three angles of a triangle, they need to sum to 180 degrees. So when you solve that equation for X, you find that your angle is 130 degrees. Number 5. Nancy's rectangular garden is represented in the diagram below. Okay, so she's got a walkway going across the diagonal. One of the sides is 8 feet and the other side is 15 feet. If a diagonal walkway crosses her garden, what is its length in feet? Okay, Well, the first thing I notice is that when you draw that diagonal, you get this nice right triangle here, and they show you with that box. When I'm seeing a right triangle and we're missing one side, we're always going to want to think to ourselves that Pythagorean theorem, that a squared plus b squared equals c squared. Where if we have a right triangle with legs a and b and hypotenuse c, that we could always find whatever missing side we have using that formula. So I ask myself, am I missing one of the legs, a and b, or am I missing the hypotenuse? In this case, we're missing the hypotenuse because that's the side across from the right angle, or the longest side in the right triangle. So I set up my equation, 8 squared plus 15 squared equals x squared, and I solve from there. 8 squared plus 15 squared is 289 equals x squared. I take the square root, Now sometimes we'll need to simplify this and put it in simplest radical form. But in this case, 289 is a perfect square. And we find that x is equal to 17 feet. For number 6, the rectangle shown below has a diagonal of 18.4 centimeters and a width of 7 centimeters. To the nearest centimeter, what is the length x of the rectangle? So again, this is a Pythagorean theorem problem because in a rectangle I have right angles. So this on the right here is a right triangle. And I ask myself, am I missing the hypotenuse or am I missing one of the legs? In this case, I have the side across from the right angle, so I'm missing one of the legs. So when I set up my equation now, my x squared is going to go on the left side of the equal sign, and my 18.4, or my hypotenuse, is going to be squared. So I get x squared plus 49 equals 18.4 squared, which is 338 and 56 hundredths. Subtract 49 on both sides, and we followed the same process as before. But you should notice that the number we get now isn't a perfect square anymore. So that when we take the square root to get x by itself, we're going to end up with something that is an irrational number. So we're going to have to round here. So when I plug this into my calculator, I get 17.01646. And it says to the nearest centimeter. So that means to the nearest whole number. So in this case, I could just round to x equals 17 centimeters. Number 7. An overhead view of a revolving door is shown in the accompanying diagram. Each panel is 1.5 meters wide. What is the approximate width D, so this distance right here, the opening from B to C? Well, again, I notice this is a right triangle, and I'm missing the hypotenuse. So I set up the equation just like I did for number 5 above. 1.5 squared plus 1.5 squared equals my hypotenuse squared. So each of my legs squared equals my hypotenuse squared. So I get 4.5 equals x squared. Take the square root on both sides, and I'm left with x equals 2.12 meters. Now it says what's the approximate width of D, so they don't tell me where to round to, so I'm going to leave it to the nearest hundredth. For number 8, what is the length of the altitude of an equilateral triangle whose side has a length of 8? So remember, an equilateral triangle has 3 equal sides, or 3 congruent sides. So each of those sides is going to be 8 in length. And it says, what's the length of the altitude? Remember how important that vocab is. Altitude is perpendicular to the opposite side. So you could pick any vertex. I'm going to pick this top vertex right here. And I'm going to draw an altitude in that makes a right angle with that base. And I see I've got a right triangle right here, but I have the hypotenuse. I'm looking for a leg, but the question is, what is the length of this leg right here? Because if I'm missing two sides, I can't plug into the Pythagorean theorem. So, when I'm looking at this, if I drew it a little bit more accurately, the altitude of an equilateral triangle is the same line segment as the median, which, remember, hits the midpoint of the opposite side. So if it hits the midpoint of the opposite side, this piece would be 4, and this piece would be 4. Now we have another side to plug into the Pythagorean theorem. So one of the legs squared plus the other leg squared equals the hypotenuse squared. X squared plus 16 equals 64. 64 minus 16 equals 48. Take the square root, take the square root. And now, even though 48 isn't a perfect square, I can still rewrite it to make it a little cleaner. You could round to the nearest hundredth, but I'm going to leave this in simplest radical form. So I asked myself, what perfect square goes into 48? And 16 does exactly 3 times. So I could break up radical 48 into radical 16 times radical 3. And radical 16 is just 4, and there's nothing I could do with radical 3, so I would leave it in simplest radical form. Number 9. Which set could not represent the lengths of the sides of a triangle? Remember that the sides of a triangle need to satisfy the triangle inequality, which states that the sum of any two sides always needs to be greater than the third side. So A plus B needs to be greater than C, A plus C needs to be greater than B, and C plus B needs to be greater than A. So all three of those need to hold true. So if I'm looking for one that cannot represent a triangle, I'm just looking for a counterexample. So it just needs to violate one of these inequalities. So if I'm looking at something like number 1, for example, well, 3 plus 4, is that greater than 5? Yeah, 7 is greater than 5, that checks out. 4 plus 5 is greater than 3, that checks out as well. And 3 plus 5 is 8, which is indeed greater than 4. Okay, so that checks out. If we take a look at number 2, though, 2 plus 5, is that greater than 9? Well, 2 plus 5 is 7, and no, that is not greater than 9. So 2, 5, and 9 cannot possibly represent the lengths of a triangle. So if I have, let's say it's 9 inches, 9 inches would be there. I would attach the 2-inch side right here, and I would have a 5-inch side right here. And the problem is, no matter how hard you push them, you just wouldn't be able to get them to close in on each other. There'd be a gap in the middle there. So the sum of the two sides always needs to be bigger, strictly bigger, than that third side. For number 10, if two sides of a triangle have lengths 4 and 10, the third side could be 8, 2, 16, or 4. So remember that the sum of any two sides needs to always be greater than the third side. So I'm just going to try each of them out and see which works. So I'm going to start with 8. So 4 plus 8 is greater than 10. 4 plus 8 is 12. That works. 10 plus 8 is greater than 4. That works. And 4 plus 10, is that greater than 8? Yes, that works. So if two sides of the triangle are 4 and 10, could 8 work? Yeah, absolutely. Now, in order to narrow down the range for these, so you don't have to try all of them, remember that in order to find the greatest value our side can be and the smallest value our side can be, we can add the two sides and subtract the two sides to figure out what our middle side needs to be in between. So 10 minus 4 is 6, and 4 plus 10 is 14. So x needs to be between 6 and 14. Can't be equal to 6 and can't be equal to 14. It needs to be strictly between there. So if x is 6.11111, that's going to be fine. Notice that 2, 16, and 4 don't fall within this range. Because what happens is, if you look at a side like 16, which is not the correct answer, when you add 16 and 10, that's greater than 4. Okay, so that works. When you add 16 and 4, that's greater than 10, so that works. But when you add 4 and 10, that is not greater than 16. 14 is not greater than 16. So one of those inequalities fail, so we can't make a triangle with those sides. Number 11. In triangle RST, the measure of angle R equals 58, and measure of angle S equals 73 degrees. Okay, so I'm going to draw a triangle RST. It's not going to be to scale. I just want to have a picture to look at so I could fill in these angles here. So R is 58 degrees, S is 73, and I can always figure out the third angle in a triangle just by subtracting the sum of my other two angles from 180. So 180 minus 58 plus 73 is equal to 49. So that other angle is going to be 49 degrees. Okay. And it says which inequality is true. And it's trying to compare all the lengths of the side. So remember that the greatest side is across from the greatest angle, or the largest angle. And the same is true for small sides. So the smallest side is opposite the smallest angle. So I'm looking at this picture right here, and I notice that 49 degrees is my smallest angle. So across from that is side RS. So RS has to be my smallest angle. My smallest side. And then my next smallest angle is angle R, this 58 degrees. So the middle side has to be side TS. And the largest angle, that's 73 degrees, is right across from the largest side, RT. So the correct answer here would be choice 4. Number 12. Find the largest side of the triangle, not drawn to scale. Okay, so just like the last problem, we need to figure out what all the angles are in order to figure out what the largest angle is, and the largest side is going to be across from the largest angle. So, first thing I notice is I have a pair of supplementary angles here. So if I just subtract 136 from 180, I find that this angle A right here is 44 degrees. And now to find angle B, I just add up my remaining two angles and subtract from 180. So 180 minus 44 plus 71 is going to be 65 degrees. And now just looking at my picture, I see that angle C is the largest angle here. So the largest side is across from that, which is side AB. Number 13. Find the value of x. Okay, if you remember the exterior angle theorem that states when I have an angle on the outside of a triangle formed by extending one of the sides past the vertex, that angle is always equal to the sum of the remote interior angles. Now, the remote interior angles are just the angles that are inside the triangle that aren't the one that's supplementary to that exterior angle. So it's going to be the other two angles that aren't this blue angle right here. So 55 plus x is equal to 116. Subtract 55 on both sides, and we get x equals 61 degrees. And that's the missing angle there. A ladder is against a building. The angle it makes with the ground is twice the angle it makes with the building. How large is the exterior angle formed between the ground and the ladder? Okay, so this one's a little trickier. So I have the ground. I've got some sort of ladder going up. It hits a building. Here's my building. And it says the angle it makes with the ground, so this angle right here, is twice the angle it makes with the building. So twice this angle. So I'm going to label this angle that it makes with the building as x, and the angle it makes with the ground as twice x, or 2x. And it says how large is the exterior angle formed between the ground and the ladder. So it wants to know about this angle right here. So we need to analyze this a little bit more than we did for the last one. Notice the picture I drew here. I've got a ladder slanted up against the building going straight up compared to the ground. And if you think about any time you have a building, it's always sticking straight up out of the ground or is perpendicular to the ground. So you've got that 90-degree angle there. Now, if you want to set up an equation to solve for what x is so you could figure out what that exterior angle is, you can just add up all the angles in the triangle. 90 plus 3x equals 180. Subtract 90 on both sides to get 3x equals 90. Divide by 3 to find that x equals 30 degrees. So if x equals 30 degrees, then twice x is going to be 60 degrees. Now notice that the interior angle next to that exterior angle is always going to be supplementary to it because they form that straight line, just as the result of extending that side outward. So I can set up 60 plus y equals 180, where y could be that exterior angle there. Notice that I'm not using x again, because we already used x, so don't use x again if you've already defined it, because x is 30. We need to use a different variable here. Subtract 60, and we find that that exterior angle is equal to 120 degrees. Number 15. In triangle ABC, an exterior angle at C measures 50 degrees. Okay, I'm going to draw. So let's see. Oops. Got a triangle. We'll call it, make it a little bit more accurate to what we have here. Okay. Not a great triangle, but you get the picture. A, B, C, and you've got an exterior angle at C, so I'm just going to extend that side. This angle right inside here is 50 degrees. If the measure of angle A is greater than 30 degrees, which inequality must be true? So if the exterior angle here is 50 degrees, the interior angle here is 130 degrees, because remember they need to be supplementary. And let's see if that helps us. I'm going to look at answer choices 3 and 4 first. The measure of angle BCA. So BCA, that black angle I just measured there. That's not going to be less than or greater than 130 degrees. I know it needs to be strictly equal to, because I already know the exterior angle there. So the question is what to do about angle B. Well, I know that angle C, or angle BCA, is 130 degrees. And A has to be greater than 30 degrees. So I'm just going to pick an angle for A. I'm going to pick 35 degrees. And for right now, we're going to call that the measure of angle A. And if the measure of angle B is x, I'm going to set that equal to 180, just to see what happens here. So when I combine like terms, subtract 165 on both sides, we're left with that x is equal to 15 degrees. So I know that fits answer choice 1 right there, that b is less than 20 degrees. Let's think about why this inequality here fails. I know I need all the angles to add up to 130 degrees. Let's say I've got that 180 degrees they need to sum to. So let's say I've got the 130 degrees we already know is there. Let's say measure of angle A is 31, so even smaller, and we're still looking for angle B is equal to 180. The measure of angle B can't be more than 20 if it was 21, let's say, because then the angle sum would be too high. So answer choice 2 doesn't make any sense. Based on this algebra that we did over here and over here, the measure of angle B has to be less than 20 because of this constraint placed on A. Number 16. In the diagram below of triangle ABC, AE is congruent to BE, so I'm going to mark that. AF is congruent to CF, I'm going to mark that with 2 dashes. And CD is congruent to BD. Point P must be the centroid, circumcenter, incenter, or orthocenter. Now notice that when I have pairs of congruent segments on each side of a triangle, that means that E, F, and D are midpoints of their respective sides. Remember that a segment that connects a vertex to a midpoint is called a median. So I've got 3 medians that I drew here, and the intersection of the 3 medians is called the centroid. And remember that big claim to fame for the centroid is that 2-to-1 ratio that it breaks up these medians into. Speaking of which, for number 17, in triangle SRK below, medians SC, KE, and RL intersect at M. So these are the medians intersecting at M. I know M is the centroid because we're talking about medians here. So I'm thinking to myself that 2-to-1 ratio. So it says which statement must always be true. So I'm going to start with number 4. SM, this piece right here, is congruent to KM. Well, we don't know anything about pieces from different medians. I only know that pieces on the same median are broken up in a ratio of 2-to-1. So for example, if MC is 1x, then SM, I'll make that a different color, SM would be 2x. So the ratio of 1 to 2. All right. RM equals 2MC. Again, these are from 2 different medians, and we don't know anything about them. We don't know if this picture is drawn to scale. We can't measure them. Number 2. MC is equal to 1/3 SM. So let's see. MC is equal to 1/3 SM. Well, if I compare them, how does 1x compare to 2x? Well, 1x is half of 2x. So it's not 1/3. So just by process of elimination, we could figure out that it's choice 1. But if we think about this 3 times MC, this piece right here, is equal to the whole median. Well, if you break a median into a ratio of 2-to-1, that means you've really broken it up into 3 pieces altogether. And MC is just one of those pieces. So if you multiply one piece times 3, you'll get the length of that whole median, which is just 3 times however big each of the pieces are. In a given triangle, the point of intersection of the three medians is the same as the point of intersection of the three altitudes. Which classification of the triangle is correct? This is a good question. Okay, so the intersection of the medians is the same as the altitudes. So first off, I know the medians always need to intersect inside the triangle. And I know the altitudes, when they intersect to form the orthocenter, that can sometimes be outside the triangle. And even with a right triangle, that can be right on the vertex. So I know this can't be a right triangle, and I know it can't be an obtuse triangle. Because remember, for an obtuse triangle, if I have something like this right here, if I'm trying to draw an altitude from point C to side AB, there's no way I can get there by making a right angle. So the only way to do that is by extending the side AB and drawing the altitude there. So I know that orthocenter is going to be on the outside. So it can't be obtuse either. So let's see. Can't be a right triangle. And scalene, well, we don't necessarily know that it's scalene, because what about a scalene obtuse triangle? That wouldn't work. So we're now down between the isosceles triangle and an equilateral triangle. Well, I know in equilateral triangle things are usually nice and even, everything's in the middle. For an isosceles triangle, let's say I've got an isosceles triangle that looks something like this, where this is 100 degrees and each of these base angles are 40 degrees. This is an obtuse triangle. It's isosceles, but it's also obtuse. So I know that when I draw the altitudes, they're going to intersect somewhere outside the triangle. So that doesn't help me there. So it can't be an isosceles, because it could be that it's an isosceles obtuse triangle. So the only one that works is 3, an equilateral triangle. So let's think about that for a minute. If we've got an equilateral triangle, all the sides are congruent, all the angles are congruent. When you draw those altitudes, remember what we said earlier in the packet. The altitudes for an equilateral triangle are the same lines as the medians. So the altitude, each of the altitudes is equal to each of the medians in an equilateral triangle. So I know they're going to intersect at the same point because they're the same line segment.